Hi there, it's Sally here, your maths tutor. I have worked through the OCR AS level 2019 paper. I would recommend that you have a look at the paper, look at the questions and have a go at them. So pause the video on each question and see what you would make of it before you just watch me walk through it. Or you could have a go at the whole paper and then watch the video. Okay, good luck, enjoy. So this is number one. It's just a series question. You've got to put in r is equal to 1 to 100 and each of these terms. So the good thing to do is to start write a few out, get a feel of what's going on. So when r is equal to 1, you'll have 1 over 1, which is just 1, minus 1 over, when r is 1, 1 plus 2 is going to be 3. And then r is equal to 2, so you'd have plus 1 over 2½ minus 1 over 4. So notice when the r is even, the number on the bottom is even, and then 2 more still even. Then when r is equal to 3, you'll have 1 over 3 minus 1 over 5. r is equal to 4 plus a quarter minus a 6. So it's going to alternate as it does in the formula there. And then you'll have plus dot dot dot, and let's see what's happening at the end. So we take it all the way up to maybe r is equal to 97, 1 over 97 minus 1 over 99 plus 1 over 98 minus 1 over 100 plus 1 over 99 minus 1 over 101 plus 1 over 100 minus 1 over 102. So you can see what's going to happen is this second term when r is 1, second fraction minus a third is going to cancel with r equals 3 a bit further along in the series. You've got the quarter there with r equals 2. It's always the second term will cancel with the first term later on. So we'll have this second term cancelling with something later on, and so on and so on. And so there'll be something before that will cancel with the 1 over 98 and something with the 1 over 97. So you're going to be left with the minus 100 and the plus 100. You're going to be left with just these two terms and these two terms. So you're going to have 1 plus a half minus 1 over 101 minus 1 over 102, and if you put that all in a calculator it comes to 1.4803. Now it specifically says 4 decimal places, so that is the answer to 4 dp. So number 2, this is a roots of polynomials question. So the roots of the original quadratic are alpha and beta, so x equals alpha, x equals beta, and they have been transposed. There's been a transformation where we've doubled and taken away 3. So what you have to do when you've done a transformation to the x coordinate is unravel that and then put it in the original going forward, the unraveled version, into the original quadratic, and then that will get you the same y answer because you've unraveled it. So what we do is, if you say x is going to be those roots, and we just use another letter, so let w equal the transformation that's happened to x. We've doubled and take away 3. If we inverse that, so it would be w plus 3 all over 2, and we put this in as x into the original quadratic, we've unraveled it, and so we put it back in going forward, then that will have the same effect to give us the same y answer. So all you need to do is do 3 and then w plus 3 over 2 all squared, minus x, which is now w plus 3 over 2 plus 2 is equal to 0. Now that first squared term, you'd square top and bottom, so you're going to have a 4 on the bottom. So if I times by 4 throughout to go clear of fractions, I will have 3w plus 3 squared minus, then the 4 will cancel, I'll have a 2 here, front of that bracket, 2w plus 3 plus 8, and then 4 times 0 is still going to be 0. Squaring out that bracket, you've got w squared plus 6w plus 9 minus 2w minus 6 plus 8 is equal to 0. Multiply the 3 in, 3w squared plus 18w plus 9 minus 2w minus 6 plus 8. Collect like terms, 3w squared plus 18 minus 2 is plus 16w. Oh, that's not 9, is it? It's 27. Up 27, down 6, 21, up 8 is plus 29 is equal to 0. So that would be one method of finding it, but you could use another method. So you could use the sum of the roots and the product of the roots. So the sum of the original roots is minus b over a, which is b is minus 1, a is 3. So minus b over a would be 1/3. The product of the roots is going to be c over a, which is 2 over 3. And we're going to use those two quantities to then deal and think about the new roots. So we sum the new roots, 2 alpha minus 3 plus 2 beta minus 3 is equal to 2 alpha plus beta minus 6. And we know what alpha and beta is. That is a third. So that's 2/3 minus 6. And 6 as thirds would be 18 thirds, so altogether 2/3 minus 18 is minus 16 thirds. So that's looking a little bit like this 16 over here. And then if we do the product of the new roots, 2 alpha minus 3, 2 beta minus 3, multiplying those together, you've got 4 alpha beta minus 6 alpha minus 6 beta plus 9. Alpha beta is this quantity here, 2/3, so it's going to be 4 times 2/3 minus 6, and this would be minus 6 of alpha plus beta, which we know is going to be minus 1/3, so it's minus 6 times 1/3 plus 9. So 4 times 2/3 is 8/3 minus 6/3 plus 27/3. So 8 minus 6 is going to be 2 plus 27, that's 29 over 3. So these, sum of the new roots is going to be minus 16 over 3. The sum of the new, the product of the new roots is 29 over 3. So they can just go into our quadratic, which is 8 squared. This is equal to minus b over a. So we have got plus, we need to change that sign, 16 over 3x plus 29 over 3 is equal to 0. And then just times by 3 and we will get the same answer. So there you've got two methods to get the same answer. I probably prefer the first method, but you've got the two methods there to choose which one you prefer. So number 3 is a matrices question. So for part A, to find AB, because we're given B inverse A inverse is 2, 1 minus 1, 1, we need to use the fact that AB inverse is equal to the B inverse A inverse. So because the given vector is AB inverse, we need to just find the inverse of that, and that will be AB. So AB is just going to be 2, 1, minus 1, 1, the given matrix, and we need to inverse this. We can just use this fact. You can watch a proof of it. I'm not going to do that here, but that is just something that you can use. So AB is going to be the inverse of the given vector. Okay, so to find the inverse, we need to find the determinant. So to find the determinant, that's just a scalar amount that for any matrix you can find by doing this diagonal minus this diagonal. So 2 times 1 is 2. So the determinant is equal to 2. minus minus 1, which is equal to 3. Now for the inverse, you need to do the reciprocal of the determinant, so that would be 1/3, that's the scalar, in front of, and then what you do for the inverse, you swap these two elements, so that will be 1 and 2, and you change the signs of these two elements, so that will be 1 minus 1, and that will be AB. It's the inverse of the given vector. Right, part B, given that A is equal to 1/3, 1, 0, 1, find B. Well, we're going to use what we found in part A, and what we need to do is do A inverse, pre-multiply by inverse on AB. Now AB we found in part A. We're given that A is this, so if we find the inverse, then these two on the front will act as the identity matrix times B, which will just equal B. So what we need to do is find the inverse of the given vector in part B, A, and then just multiply it by our answer from part A. So the inverse of A is going to be the determinant again. We need to times these two diagonals. So 1/3 times 1 is a third. Take away these two diagonals, which has got the naught. So the determinant is going to be third. And the reciprocal of that is going to be 3. And then we need to do the same again. We need to swap that diagonal elements and then change the sign of these two. So we need to take that inverse and times it by our answer from A. So we're going to have, now what we can do with the 3 and the third, they can come on the front, because these two determinants on the front, they can go 1/3 times 3, and then we need to do A inverse 1 minus 1 naught 1/3, and times it by our 1 minus 1, 1, 2. So they're going to cancel in the front. And then in order to times the two matrices together, you just times the row with the column. So to get this first element here, we need to do 1 times 1 and add to it minus 1 times minus 1. So 1 times 1 is 1, minus 1 times 1 is going to be 0, so the actual element is going to be 0 for there. Then the next one, you do the same. To find this top element, you need to do 1 times minus 1, so it's minus 1, plus minus 1 times 2. So 1 times minus 1 is minus 1, minus another 2, so that's going to be minus 3. Then do the same on the bottom. You need to times along here and then times along the row. So to get this first element, it's going to be 0 times 1 plus 1/3 times 1, which is 1/3. And then you're going to have 0 times minus 1, 1/3 times 2/3, so it'll be 2/3. So that will be our answer for B. So not everybody's favourite thing to do. Number 4 is finding the inverse of a 3 by 3 matrix. Now there's quite a bit to it. The first thing you need to do is to find the determinant. So what you do is you take all the members from the top row in turn. So you take 1, I just write A here, so 1, and then you cross out the rows and columns that they are in, and that will give you these left, and that is called the minor matrix, and we find the determinant of that. So if we just write it down here, 1, 2, 1, 2. And then it alternates in signs. You have to then take away and take the next one along, cross out the rows and columns. So it's going to be minus 2 times the determinant of what is left when you've crossed the rows and columns out. So that's minus 1, 2, minus 2, 2. And then the last one will be a 3 and you plus. So you alternate the signs as you go along that top row. So 3, cross out again, and then it's going to be minus 1, 1, minus 2, 1. So that is going to be the determinant of M. So if we now find these individual determinants of the minor matrices, what you do is you times that diagonal and you take away that. So because those diagonals are the same, that first one's going to be 0. Then this one is going to be minus 2 minus minus 4. So that's going to be plus 2 times the minus 2 on the front, which will be minus 4, minus 1, minus minus 2, which is 1, so it'll be plus 3. The determinant is minus 1. So what you do with that number, you have to, the times on the front to the inverse matrix, the reciprocal. So the reciprocal of minus 1 is still going to be minus 1. So that goes on the front. Now what you do is you have to take every element in the 3 by 3, so there's 9 elements, and wherever they are, you do the same thing. You cross out the rows and columns and you find a matrix of minors for all of the 9 elements. So let's just do that again. The 1 is going to be 1, 2, 1, 2. Well, this top row is just going to be the minors that we've just found. So I'm just copying them in that we've just found them. They are from down there, from when we found the determinant. So let's go on the next row. Cross out, you're going to be left with 2, 3, 1, 2. And then if you do all of these, we move along, you're going to have 1, 3, minus 2, 2, 1, 2, minus 2, 1. And then the last row, 2, 3, 1, 2. And then 1, 3, minus 1, 2. So it's quite repetitive, and you just have to do that crossing out and see what you're left with. And I write them all out so because it's so easy to go wrong with signs and stuff. But now work out all those determinants. So the first one again is that column minus that column is going to be 0. Then we had all these before. Minus 2 minus minus 4 is going to be 2. The next one is 1. Here 4 minus 3 is going to be 1. And if I just fill all these in, 8, 5, 1, 5, 3. So that's the matrix of minors. Then you've got to find the cofactors, and a bit like the change of signs with the determinant, it goes plus minus plus, then minus plus minus, plus minus plus. So you have to change the signs according to that pattern. So it's going to be 0, minus 2, 1, minus 1, 8, minus 5, 1, minus 5, 3. And then we've got the determinant that goes on the front. Plus, it's minus 1. So everything in there is going to change sign. So that will be 0, 2, minus 1, 1, minus 8, 5, minus 1, 5, 3. So that's taking that minus into every element. And then you have to transpose that. So that means the row now becomes the column on the inverse matrix. So finally we can do M inverse is taking that 0, 2, minus 1 will now become the first column instead of the first row. 0, 2, minus 1. Next one will be 1, minus 8, 5, and then minus 1, 5, 3. And that is your inverse matrix. We'll just check. Yeah, that is the correct one. Right, so we'll get rid of these and we'll have a look at part B. Okay, part B. Now, here are the equations of 3 planes. So they're in 3D, so that is the equation of the plane, and we want to know where they intersect. Now, what you've got to notice is that the coefficients of all these planes, 1, 2, 3, minus 1, 1, 2, are the coefficients, are the same as those elements. So if we took the given matrix 1, 2, 3, minus 1, 1, 2, minus 2, 1, 2, that's M, and times it by X, Y, Z, out would come 19, 4, and K. Because if you times those two matrices together, you'll get 1 times X, 2 times Y, 3 times Z, which will give you that first equation of the plane. So this system of equations is going to be solved by looking at these matrices. Now we've got the inverse. What we need to do is do M inverse times X, Y, Z. So, sorry, not M inverse, but have M inverse first and then M, and that's going to equal M inverse 19, 4K. So what we've done is times by M inverse at the front, and these two times together are going to be the equivalent of the identity matrix, and then that will give us the solution. We'll find where they all meet in terms of K. So all we need to do is take our inverse matrix, 0, 1, minus 1, 2, minus 8, 5, minus 1, 5, 3, and just get rid of it there, and times it by the 19, 4K, and out will come the solution in terms of X, Y, and Z. So we're going to have 0 times 19, 1 times 19 minus 1 times 4 minus K. So that's going to be 4 minus K is equal to X. Taking the second row, 2 times 19, which is 38, minus 4 times 8, minus 8 times 4, which is minus 32, which will be 6. So 6 plus 5K is equal to Y. And then the next row, minus 1 times 19, minus 19 plus 20, so that's 1 plus 3K is equal to Z. And that is all you need to do. Hence find in terms of K the point of intersection. So that'll be the answer there. Right, part C. We've split these up and gone onto a different page, but let's just get rid of some stuff here. Part C. Now this is all about the angle between two planes. So you've got two planes. If I just draw them to demonstrate, P1 maybe and P2. Now we're looking for the angle between them, but that is going to be the same if I have, here's P1 here, and if I draw here where they cross the normal to P1 and draw here the normal to P2, we're actually looking for this angle here, the angle theta between the two planes. But because P1 and its normal make 90, this angle here is 90 minus theta. Then because P2 and its normal make 90 degrees, then 90 minus the theta, this is going to be theta. So what you're looking for, the angle between the two planes, is the angle between the two normals. Now the normal vectors are just the coefficients of all the x, y, z. So the normal for the first plane is 1, 2, 3, and the normal for the second plane is minus 1, 1, 2. So all you need to do is use the dot product formula that the angle, cos of the angle, is equal to n dot n divided by the modulus of the two normals times together. So cos theta is going to equal, those normals were 1, 2, 3, dotted with minus 1, 1, 2, all over square root of 1 squared plus 2 squared plus 3 squared times the square root of minus 1 squared plus 1 squared plus 2 squared. And when you do the dot product, you just times the two i's together. So 1 times minus 1 is minus 1, plus 2, which will be 2, minus 1 plus 2, which will be 1, and then 3 times 2 is 6. So on the top, you're going to have 7 divided by root 14 root 6. You put that in your calculator and you do inverse cos of it. Theta comes out to be 40.2 degrees, or if you want to do it in radians, 0.702 rads. Okay. Right, number 5 is a proof by induction question. So they follow the same pattern. You have to prove that it's true for when n equals 1. Assume it's true for any old n equals, and we usually use the letter k. Assume that that holds true, and then show that it holds true for the one further along from k, so k plus 1. So we've got this series here, and we have to show that it's true for n equals 1. So when n is equal to 1, you will have 1 over 3 to the 1, which will just be 3, is equal to a half 1 minus 1 over 3. So that's a half. A whole 1 minus a third is going to be 2/3. And you can see the 2's here will cancel, so it does hold true. So true for when n equals 1. So we're going to assume now true for when n is equal to k. So we've got here from r is equal to 1 to some k, 1 over 3 to the r is equal to a half 1 minus 1 over 3 to the k. So you've just substituted in that it's k terms along, and so all the n's have now become k's. So now we need to prove that it's going to be true for k plus 1. So if we have the sum from r is equal to 1 to k plus 1 of 1 over 3 to the r will equal r half 1 minus 1 over 3 to the k. That is the sum up to the k terms plus one more term. Well, one more term using this will be 1 over 3 to the k plus 1. So you've got the original up to k, and then one more term will be 1 over 3 to the k plus 1. So this is going to equal a half. Now what we need to do is make these powers the same. So if I want to say 1 over 3 over 3 to the k plus 1, I've multiplied by 3 on top, so I've got to add one more below. So that 3 will cancel with that plus 1 in the power and give us back to this term. And then I need to incorporate this into the bracket, so I'll need to have plus a 2 because we've got the half outside, so when that half multiplies in, it will cancel with that 2, and over 3 to the k plus 1. So now, because these powers are the same on the bottom, it's going to be a half. We've got our 1 down 3 of 3 to the k plus 1, and plus 2 will be minus 1 over 3 to the k plus 1. So it's in the same format as we've had before, so it's true now. So true for n is equal to k plus 1. So if true for n equals k, and then true for n equals k plus 1, it's true for all n. Okay, that's proof by induction. Question 6 is a transformation matrices question. You're given M, you're told that the determinant is bigger than 0 for all lambdas. So let's find the determinant of M. Remember, it's this diagonal minus this diagonal. So this diagonal means you've got to times those terms together. So it's lambda into lambda minus k minus k. Now you're told the determinant is bigger than 0, so this expression that is the determinant must be bigger than 0. So let's multiply it out. Lambda squared minus k lambda minus k. Now we've got a quadratic in terms of lambda. Now a quadratic to be bigger than 0, you think of your graph, then it's going to be bigger than 0. The whole of the graph is above the x-axis. It's got no real roots, and therefore the discriminant b squared minus 4ac must be a negative when we've got no roots. So let's do the discriminant of this quadratic in terms of lambda. B is minus k, and we've got to square it, so that will be minus times minus, it'll just be k squared, minus 4 times 1 times minus k. It's less than 0, so k squared plus 4k has to be less than 0. So now you've got a quadratic in terms of k, and if you think about that, taking k out and k plus 4, where would that be graphed? It's going to go through 0 and minus 4, because if you think of the critical points where it's going to equal to 0 when k is the opposite of this bracket, so k is minus 4 and k is 0, and therefore where does this quadratic go less than 0, this bit underneath, as long as k is between minus 4 and 0. So it's that section there for k, and then the graph will be low. So that is the range for part 1 of part A. Right, let's do part 2. What is the significance that the determinant is bigger than 0? Well, the determinant is a scalar quantity that we can evaluate by doing those diagonals, but the quantity is the scale factor when we do use the matrix as a transformation. So the determinant determines how bigger the area of the new shape will be. But when the determinant is bigger than 0, just like scale factors, when you're enlarging them, they're the same size of the center. So a determinant bigger than 0 means that the image will be not flipped, and it will be oriented to the same way. So determinant bigger than 0, the image will not be flipped and orientated the same. Right, now for the rest of the question, we take that k is equal to minus 2. So let's have a look at B. Determine whether there are any lines through the origin that are invariant for the transformation t. Now it tells us it's a linear transformation. When you have a linear transformation, then the origin stays still. That's one of the definitions of a linear transformation. So we know that the origin is going to stay still. So is there any invariant lines that are going to go through the origin? Now, when you have something changing, say you've got a point going under a transformation over here, and you'll have a whole set of points staying on the same line. Invariant points means they stay still, but an invariant line means that that point can go to a further along point, but it's got to be on the same line, and the line is a straight line, y equals mx plus c. So let's put minus 2 in the matrix. So we've got lambda and then minus 2, 1, lambda minus minus 2, which will be plus 2. when we multiply that by a point x, y, now if we were doing invariant points, then you just get the same point, but we're doing invariant lines. So it doesn't necessarily need to be the same point, it just needs to be a point on that same line. Now what you do, you don't call it y because we don't want to have too many variables. You call this mx plus c because that is y, and that needs to go along the same line. So we need, could be a new x, could be the same x, but it also needs to go on this same line. So using m and c, mx dash plus c. So if we times these two together and equal it to the invariant line point, and then see where we're at. So you column, a row with the column, so you've got lambda x minus 2 into mx plus c is equal to our x dash, and then go to your next column, multiply by the row, you've got x plus lambda plus 2 times mx plus c is equal to our new y point, x dash plus c. Now again, we've got too many variables, so what we need to do is use this for x dash and put it in here for this x dash, and then see where we're at. So we've got x plus, now foiling this out, you'll have lambda mx plus lambda c plus 2mx plus 2c is equal to m. Now we're using this as our x dash on the top line, lambda x minus 2 mx plus c. So let's have a look at the right hand side. You've got m lambda x minus 2 mx minus 2c, and then take the m in, lambda mx minus 2m squared x minus 2mc, and that's equal to everything on the left. So okay, so what does this look like? Because we've got this quadratic term, let's try and see if we can get everything to one side and order it up with our quadratic term first. Now, is there anything that can cancel? We've got a lambda mx on both sides, so that can cancel. Just tidy things up before we get going. Nothing else will cancel. So bringing this 2m squared x over the other side. And then let's see what other terms we've got in x plus 2mx. So I've done this term and this term and this term. So then I'll have a plus lambda c plus a 2c and plus a 2mc is equal to 0. Now if I take x out as a common factor here, I'll have a 2m squared plus a 2m plus a 1 plus a lambda c plus a 2c plus a 2mc equals 0. Now, having this expression here, because this represents the y-coordinate of the new line, then it's so many x plus c. These can all group together and just be one constant, but this represents the gradient, and because 2m squared plus 2m plus 1 I can't factorize, that has got no real roots. So therefore, I'm not going to have any invariant lines. So there's no invariant lines. Right, part C. The transformation T is applied to the triangle with area of 3 units. The resultant image is 15. So 3 units goes to 15 units squared. So that's a scale factor of times by 5. So that's telling us that 5 is equal to the determinant. So what was our determinant before? We've got putting back the k is minus 2, 1 lambda plus 2. The determinant of that is lambda plus 2, minus 2, so that's plus 2, must equal 5. Lambda squared plus 2 lambda plus 2 equals 5. Lambda squared plus 2 lambda, taking the 5 over, minus 3 is equal to 0. That will factorize lambda, 3 and 1, minus 1 and plus 3. Lambda will have to equal 1, or lambda equals minus 3. So question 7, Argand diagrams, the set of points for which the modulus of z, the complex number, minus 1 minus 3i has got to be all less than or equal to 3. So remember, if we do z minus and then it's 1 plus 3i is equal to 3, and then if we draw this number, so this is real and imaginary, so it's 1 along 3i, and then our given complex number has to be, when we take them away, it's got to be less than 3. It's just going to be a circle around that point, which is 1 plus 3i, and it's got to be 3. It's quite a good circle. There you go. It's got to be, the radius is therefore 3. Now in part B, the set of points for which the argument, the angle that z plus 4 makes, has got to be pi by 4, so 45 degrees. So remember this transformation, if we can go to minus 4, and then it's got to be 45 degrees from there. So it's just going to go through like that. And this really will be the equation that's going to go through at 4i, because this has got to be pi by 4. So 4 along, 4 up to make that go across at 45 degrees. So that's just the sketch for parts 1 and 2. Part B, find an exact form, the two values for which z, the first one you've drawn, and the other ones are equal. So it's going to be these 2 points here. So algebraically, it's just where the line meets the circle. So if we just put that in terms of x and y, what's the equation of the circle? Centered at 1, 3 is just going to be x minus 1 all squared plus y minus 3 all squared is equal to r squared. What was the radius? 3, so that's going to equal to 9. The equation of the line, well, it's got gradient 1 and it's going through the y-axis as 4, so it's going to be y equals x plus 4. You've got one linear and one quadratic, so we just need to substitute in that y is equal to that into the circle. So x minus 1 all squared plus x plus 4 minus 3 all squared is equal to 9. X minus 1 all squared plus x plus 1 all squared is equal to 9. Squaring these out, x squared minus 2x plus 1 plus x squared plus 2x plus 1 is equal to 9. The two x's will cancel, we'll get 2x squared is equal to, those ones on the other side are going to be minus 1, so 9 minus 2 is 7. X squared is going to be 7 over 2. X is equal to plus or minus the square root of 7 over 2. Sorry, plus or minus 7 over 2. So all we need to do is put that back in and find the y coordinates. So when x is equal to minus root 7 over 2, y is equal to minus root 7 over 2 plus 4. So the coordinate will be minus root 7 over 2, and then just make this pretty tight the other way around, 4 minus root 7 over 2 when x is equal to plus 7 over 2, y will equal root 7 over 2 plus 4, so that coordinate will be root 7 over 2 4 plus root 7 over 2. So they are the points in terms of the x and y, but all you need to do now is just interpret them as our complex numbers. Z is going to be minus root 7 over 2 plus 4 minus root 7 over 2i, or Z is going to be plus 7 over root 7 over 2 plus 4 plus root 7 over 2i. That's number 7. Right, number 8, the last question. We've got I is a root of this equation. So when you have roots, you always get the conjugate pair. So minus I is also a root. But when we have a root and we plug in that Z equals that root, then out will come 0. So if for part A, we let Z equal to I, so our equation will become I to the 4 minus 2I cubed plus 3I squared plus IA plus B must equal 0. Now if we work out what these are, I to the 4, well, minus 1 root of will be to the 4 1, and then I cubed is going to be minus I times minus 2, so that will be plus 2I minus 3, I squared is minus 1, and then it'll be plus AI, we should write that way round, plus B is equal to 0. Now collecting the real parts, 1 plus 3 is going to be minus 2 plus B equal to 0, because we are saying that all the real parts must add up to 0 and all the imaginary parts must add up to 0. So 2I plus AI is equal to 0, and this will lead us to the two things that we want. B must equal 2, and then 2I must equal minus AI, so A must equal minus 2. So there's the proof. Get 4 marks for that. That's not too hard, that one. Part B, find the other roots. So we know that I and minus I are roots, then what we can do is, because we know that these coefficients, we've got 2 here, we've got the 3, we've got A and is minus 2 and B is 2. but usually using these two because we know that the sum of the roots, now there's 4 of them, alpha plus beta are 2 we don't know, plus I minus I is equal to minus b over a, which is equal to minus 2 which over 1, which is just going to be 2. So these i's will cancel, so we know that alpha plus beta is equal to 2. And then the other one we need to use is alpha beta times I times minus I. The product of the roots is going to be, these signs go minus plus minus plus, so that'll be is equal to 2 over a, which is just 2 because a is 1. I times minus I is going to be plus 1, so we know that alpha beta is equal to 2. So what we've got now by using the sum of the roots and the product of the roots is 1 linear, 1 quadratic. So if we say from this one, do it any way round, I'll do alpha is equal to 2 minus beta and substitute in here into our quadratic. So 2 minus beta times beta is equal to 2. So you've got 2 beta minus beta squared is equal to 2. All to one side equal to 0. 0 is equal to beta squared minus 2 beta plus 2. Now here you've got a quadratic and it doesn't factorize, so we'll have to use the quadratic formula. So minus b will be plus 2 plus or minus b squared, so 2 squared is 4, minus 4ac, 4 times 2 times 1, all over 2. So this will be what our root is, beta. So beta is equal to 2 plus or minus 4 minus 8, which is the square root of minus 4, all over 2. So beta is equal to 2 plus or minus, now taking this to be under here, minus 1 times 4, and the 4 will come out of the root as a 2, so that will be 2i all over 2. So it's going to be 2 plus or minus, sorry, not 2, divide by that denominator, 1 plus or minus I. Now because we've got the plus or minus, that is actually going to be both of our roots. So the roots are I minus I, 1 plus I, and 1 minus I. Okay, that one wasn't actually that hard, number 8, but well done for getting to the end of it. We've done 8 questions. That is your Further Maths AS paper from 2019.